Hey everybody, this is Larry. This is me trying to do week two's whatchamacallit, weekly premium problem for December. I forgot to do it because I don't know when it comes up, but this is my new having premium. Apparently 3-4 days ago. I don't know if it comes up on Monday or something. I don't know. Someone tell me because or maybe Tuesday, Thursday. I don't know. Anyway, let me know in the comments if you know when they come up or unlock, or just send me a reminder next time and I'll get to it. But yeah, today's problem is, or this week's problem is 323, number of connected components in an undirected graph. So this would be useful in a recent contest problem. I had a Q4. I did the last week or the week before. I don't remember anymore. But yeah, I mean, this is a very straightforward thing. You have some edges and you have to return the number of connected components, right? I feel like I did something even similar the other day with respect to talking about this. Maybe that was in one of the extra problems that I did with respect to, counting how to do it. I think the canonical way of doing this is probably, or at least the way that I would recommend, especially depending on how you are given the input. You probably should do this with union find, and that's something that I definitely recommend. If you already know how to do it with breadth first search and you already know how to do it with depth first search, then definitely recommend trying union find. I'm lazy for this video, so I'm not going to do it that way, because I if I have to do it that way, I would have to explain it, and yeah, that's why I'm not doing it. A funny fact is that I did show off union find once, like almost 10-15 years ago in an interview. Instead of just using it was a connected components problem. It was disguised more, but it was a connected components problem, and I showed up by using union find. But then we got into this debate about the inverse Ackermann the inverse Ackermann function, or the constant, or whatever you want to say, and there was a lot of, like, whether that's constant and stuff like that. And then TLDR is that I end up not getting the job that way when I should have just done it with linear time. I think the guy was just not happy with me not being precise, even though I thought I was just doing extra credit. That's what you get for showing off. So stick to the basics is what I'm saying. So anyway, I have a coin here from Aruba. Heads, I'm going to do it with depth first search, and then tails I do with breadth first search. Let's go. Sorry, that was loud. Tails, I'm going to do with breadth first search. Okay. But the idea is still going to be the same, which is that, okay, I like big ends instead because it's whatever. But yeah, so we have a done is you go to force times n, and then we want to construct the edge list, the adjacency list, this way. Oops. And then for each edge, we put in the adjacency list, right? Just double checking that this is 0 indexed and not 1 indexed. I know that that's in one input, but just want to make sure. Okay. Because otherwise we might have to do, off by 1 maths or something like this. But yeah, okay. And then now it's actually the same as the depth first search. It's just, depth first search, breadth first search, it doesn't really matter, right? You still, because there's no rate, you just keep looking at everything. So yeah, so if not done of I, then count 1, return count. I mean, of course, this is not done, but and then here we want to traverse, or maybe just go breadth first search on I, right? And then here we can actually reuse this done, I suppose. So yeah, we can set up a queue. Done of x is equal to true. And this is part of the NQ, right? And then just q dot append t, and then while length of I have to NQ x. No, whatever. Now I just say pop left. And then yeah, for v in edges of now, if not done of v, then we NQ v, right? And that's pretty much it. I guess we don't have to view and return. I think that's pretty much it. Let's give it a spin. Oh, whoops. I usually call it edges actually. But yeah, okay, so that looks good. Let's give it a submit. And yeah, that's pretty much it. Really fast. And this is going to be linear time, linear space. And by that, I mean v plus e in both cases. Because you have to look at every e, because this will look at every e eventually. And every v will pop eventually on here. It's one, so yeah. And you need extra space here, and you need extra space here. So v plus e, linear time, linear space. And the cool thing is that if you do want to do it with depth first search, but you don't want to do it recursively, all you have to do is change this from pop left to pop, and there you go. Depth first search, easiest change ever. But as you can see, the complexity is always going to be the same for both of these for this particular problem of connected components. Basically, the idea here, just to kind of give a little bit of an example, a little bit of a background with this depth first search, is that basically looking at each node, you go, okay, let's say I start at 0. Have we seen 0 yet? No. Then you could color it in, color it black, and then we connect everything. We color in everything that's connected to this and their nodes to black, right, or whatever color. And then now when you go to 1, you're like, oh, it's already colored in. That means that we already counted this component. We go to 2, we already counted this component, and so forth until you go to 3, and then you color it again, and so forth. Yeah, that's pretty much all I have for this one. Let me know what you think. That's pretty much it. Stay good, stay healthy, to good mental health. Have a great weekend or whenever you're watching it. I'll see you later and take care. Bye bye.